All right, hello, Math 154. This is week 7, lecture 1. Just going to cover our whiteboard per usual before getting into the lecture today. So we're going to just keep pushing forward through chapter 3. So 3.1 due date you'll see in my math lab, 3.2 you'll see in my math lab. Excel 2.4 CPI. We've already talked about how this whole file might not necessarily be visible at first, that the issue is kind of fixing itself, it seems like, but just I made a memo about that anyways last time. So if you have some confusion when you open a file and you're not sure what you're looking at, and by that I mean that you don't know where you are in the file, go back and watch the beginning of last class's lecture, week 6, lecture 2. That is to say. So again, that due date will also be in my math lab. And then I am assigning a quiz today that will be due in Canvas. This is a 1-question quiz. It's titled Pay Attention. So you should see that link available in Canvas, and you'll see the due date also in Canvas. Or if you're watching this live, then you get those due dates in the live lecture, of course. And I said it will be available later today. It should already be available by the time you're watching this. That was just kind of a little memo. And I say to answer the quiz as a QR student, but no sentences or paragraphs. So I don't want a sentence. I don't want a paragraph. This is going to be a Canvas quiz, which means you get immediate feedback, unlike the video quizzes where you have to wait for me to grade them. So these Canvas quizzes, I have to build a list of answers that are correct. So like a previous quiz, for example, if an answer was, say, 2,567, I have to build the shell to accept answers of 2,567 as well as 2,567. Now, if there's extra detail in there, maybe it's 2,567 and then a word after that or a term after that, you know what I mean? So again, these things are not built for you to say, I believe that the answer is 2,567. If you say all that, Canvas is going to mark it wrong because it only expects the answer of 2,567 or 2,567, or again, maybe there's an extra word attached to that because units are important. So again, don't answer a sentence, don't answer a paragraph. Those are automatically going to be rejected. Yes, if you do that, I will be likely to go back and give you full credit for that, but you're going to have to wait for me to actually get to those. I don't see them immediately, and I don't do these until they're all already turned in. Otherwise, I have to keep going in and grading and grading and grading and grading. So again, all the important aspects of paying attention, does it make sense? Other details that are important as a QR student. So remember, we're not really doing partial credit with these quizzes for the most part. So make sure that you get this right. Make sure that you get this correct. All right, so with that being said, we're going to continue where we left off in 3.1, which was we were going to start with a quick temperature problem and then call 3.1 done, and then we get into 3.2.
3.1 stuff. Had the temperature conversions, and I threw 4 of those equations up there. Let me just really quickly. Hello. There we go. Mouse wasn't working for a second. Let's just put those back up there again. Just a couple of them though. F equals 9/5 C plus 32. That was one of them. And C equals 9/5 parentheses F minus 32. Now, these two equations are just algebraic rearrangements of each other, and also the one on the right is wrong. That should be 5/9, not 9/5. There we go. 5/9. So we have the F equals is a decimal as well, and the C equals we gave you distributed. It doesn't matter what the form looks like as long as you are able to plug a number into a formula and evaluate it. It is a very simple concept to plug a number into a formula and evaluate it, especially if we're going to give you the formula, which I already promised. So let's say, what is, and just one last example, 212 degrees Fahrenheit. Looks terrible. Converted to Celsius. So what is 212 degrees Fahrenheit in Celsius? Now you may know this answer off the top of your head. That's not the point of this. The point is plug it into an equation and see if you can get the answer. Now, since I gave you a temperature in Fahrenheit, you have to plug it into the F because that represents the temperature in Fahrenheit. So you could either plug it into this equation there, which means you're going to have some algebra to do. You'll have to move the 32 and get rid of that 9/5 somehow. Or you can plug it into this one, and then all you got to do is arithmetic because the C, the temperature in Celsius, is already by itself. So what that means is that for this problem, it's easier to plug it into the one that says C equals instead of the one that says F equals. You can get the exact same answer either way, but the right-hand one is going to be easier. So we'll get C equals, excuse me, 5/9, parentheses, 212 minus 32, and then you close your parentheses. If you do 212 minus 32, you're going to get 180. So you get C equals 5/9 times 180. Now, yes, you could go ahead and put this in a calculator, but I've also mentioned that you're supposed to know your math with fractions, so you can reduce the 9 and the 180. 9 will go into 180 20 times, so you can say 9 goes into 9 once, into 180 20 times. And then you're just doing 5 times 20, which is 100. And you get C equals 100. Now, again, this is not an answer as a quantitative reasoning student. You don't say it's 100 degrees. First of all, you don't say it's just 100. Second of all, you don't even just say it's 100 degrees. You would say it's 100 degrees Celsius. That's the answer as a quantitative reasoning student. Hint, wink, nudge towards something I just mentioned that you have to answer as a quantitative reasoning student. I didn't just say 100. Hint, wink, nudge. Now, spoilers, the answer in your quiz, or the question in your quiz has nothing to do with temperature, so you don't worry about like, well, how do I put this little degrees symbol in Canvas? Don't worry about that. It's a much simpler idea there. So that's temperature conversions. Again, we said that temperature conversions are not proportions. So the idea of dimensional analysis, which is what we heavily focused our ideas on in 3.1, does not work. You can't just say out with the old and with the new. You can't multiply by a fraction where your old units are in the bottom and the new are in the top. It does not work because 0 degrees Fahrenheit is not 0 degrees Celsius. So the whole idea of one thing doubling and the other thing doubling falls apart. All right. Also, that means you can't use the proportions version of it. These aren't inversely proportional either. It's nothing to do with proportions. Temperature conversion is just a fancier formula. And this idea right here, especially with the F equals, this is something we're going to start studying a little more heavily in chapter 5, where you've got a number paired with a variable and then another number just by itself. This is what we call a linear model with a fixed amount and a variable amount, but we'll save that discussion for another day. And the idea starts with proportions here. This part, if we only had that part, then it would be proportional, but it's the 32 in this instance that makes everything not proportional. So I had said that some of you may have known that 212 was already the answer, which is 100 degrees Celsius, because that's just one of the two conversions that actually established the equation. When someone decided to make Celsius, because Fahrenheit was the OG in this instance, they said, all right, we want to make the water freezing temperature of 32 degrees Fahrenheit. We want to make it 0 degrees in this new thing for simplicity. And then when water boils, which was traditionally 212 degrees Fahrenheit, we want that to be 100 degrees for simplicity, because Celsius, like every other European conversion, meters, liters, all that stuff, they're all based on powers of 10, because powers of 10s are easier ultimately because we count with our fingers and toes traditionally, and most of us have 10 of each. So that's actually the entire reason we have a counting system based on 10. If all of us were born with 8 fingers and 8 toes, we would count 1, 2, 3, 4, 5, 6, 7, and then it would be 10. There would be no 8 and 9. And then we'd go 11, 12, 13, 14, 15, 16, 17, and then we'd be at 20. And that sounds really freaking weird, I know, but that is the entire reason we count in tens. It's because it's what we have on us, traditionally speaking. All right, so that's 3.1. 3.2. And if you are actually going into these notes and reading ahead like you're supposed to, which at this point I have no idea who is. I think I probably need to do a quiz ahead of time on that at some point soon. It seems like a good idea. You will have noticed that 3.2, I hardly have anything typed in this. It's 3.2, it's 4 or 5 lines, and then 3.3. So this is a pretty short section. We will still have a nice little, we'll pull something from the guided worksheets, which let me go ahead and open that up. I was fighting my computer this morning, so I didn't have time to open this, sign in, and get those worksheets open, and then we'll start our talk. Maybe we'll see the guided worksheets. I might just have to write them up. Luckily, I have the printed version in front of me. All right, cool. There we go. All right. So scales, wrong thing. Scales. A model scale is a ratio. Oh, look, ratio. We spent all of chapter 2 dealing with ratios. Well, I would say like 85% dealing with ratios because inverse proportions are technically not a ratio when you set them up accurately. If you set them up inaccurately, they can be a ratio, but that's a horrible idea, and don't do that. But that's inverse. Notice I said inverse, not direct or not just proportions. Attaching inverse changes the game. So most of chapter 2 we spent dealing with ratios. Back in the last section, we were dealing with proportions, which are just ratios. We learned dimensional analysis, which was just another way to handle proportions. Interesting. So a model scale, the stuff in 3.2, is more ratios. Everything in chapters 2, 3, and 4 is based on the concept of ratios. When we get into chapter 3, ratios are still a part of everything, but there's something else going on, and I already alluded to that a few minutes ago when I was talking about that plus 32 thing. So these ratios, they don't go away. They don't go away. This one topic is the basis of probably 3/4 of this course. So it's a ratio used to determine the size relationship between a model and what it represents. So when you open your GPS and you see the map going from your home to your destination of wherever you're going, if you're going anywhere in this world right now, you know, on your screen it only looks like maybe 2 inches, but in reality you might be going 17 miles. So there's a ratio involved there to scale the quantity of your actual distance to the distance on this map that represents everything that everything that you'll go in terms of driving. So a scale is just a ratio. So it might say something like, all right, well, 1 mile in reality is 1 inch on your map. That would be a scale. Or maybe 2 miles in reality is 1 inch on your map. Or maybe 3 miles in reality is 7 centimeters on your map. It doesn't have to be inches. It doesn't have to be miles. It could be 10 kilometers in reality is 14 inches on your map. They don't have to be ones. They can be anything. Usually we like one of those to be a 1, which is why I say the word typically. And then when I say typically, the first quantity is scaled to 1. When we say first, we're typically referring to the model. So again, this is typically, this is usually, this is almost always, but not always. So usually it's like 1 inch on the model, and then that might be 3 miles or 5 miles or 10 miles in reality. Or 1 centimeter in the model is 3 miles or 5 miles or 10 miles in reality. And again, there would be only one of those things. It just depends on how everybody set it up. And it doesn't have to be maps. When you talk about model cars and planes and action figures, if they're super realistic in terms of proportionality, then you can use this model scaling the same way. Say, oh, okay, well, I've got this car that's normally, I don't know, about 12 feet long, and the model's going to be 1 inch long. So that would be a 1 to 12 model. 1 inch is 12 feet in reality. And that's a pretty small model. That's like a micro machine, I guess, if they still even make those. I have no idea. If you don't know the reference, I'm sorry. Then there's bigger toy models. So maybe it's like 1 foot is 12 feet. So 1 foot of the model, which would be a larger model car, would be 12 feet in reality. Or maybe you've got a model airplane. So a small airplane here. So 1 inch is 72 feet on the airplane maybe, or 1 foot in the model is 72 feet on the airplane. So there's no units written here. So that's saying it could be the same units, 1 inch is 72 inches, or it could be different units, 1 inch is 72 feet. So again, typically the model quantity is scaled to 1. So when I say first here, first I'm saying is the model, the smaller of the two things, because when we make a model, we generally going to make it smaller. Why would you make a model that's bigger than the actual thing? Now, yes, there are cases where that's true. If you have something ridiculously teeny, if you're trying to make a model of, say, an atom, then you're going to increase the size. So maybe I don't want to use the word that it's rare, but it is less often, I feel like. Usually we're scaling things down, but there's certainly instances where we want to scale them up. Okay, so this 1 to 72 is a pretty common scale. 1 to 48 is also another common scale for models with like little toy planes and cars and things. That's not something you have to memorize. We would give you the scaling factors. That's what we call that constant of proportionality, which in this instance would be the 72. It's a 1 to 72. That's the scaling factor. The cool thing is, if you don't like setting up proportions where you use your words and then write the scaling factors on the other side, you can also set up a y equals kx proportion form instead of writing it fraction equal fraction. You can do this instead, and the k is that, as long as you have the actual on the left and the model on the right, unless it's the flip-flop where you're scaling something up, like a cell or an atom. And I usually have a joke that goes with that, and I'm not going to say it. Again, I'm always a little weird about my jokes, whether I want them recorded on the internet, if they have even just a touch of, what's the word I'm looking for? They're not G-rated, I guess. They're PG, but even still, you never know what'll happen 10 years from now, and I get canceled. Okay, so let's try this stuff out. Let's see how we can actually use this. And let's go big. Literally, let's zoom in and go big. No, not that big. And I'm going to, let's open up a new file. Give myself some space. That way we can do this and this. Perfect. You wish to create a scale model of the solar system. Let's maximize it for now. On your campus quad, when you're allowed to go. Well, you can still go there. You just don't go in the buildings that much. You can still go in there, I guess. That is circular and measures 240 yards in diameter. So what they're saying here is you've got a quad that is circular. It's not too often that quads are circular, but that's okay. But maybe your quad isn't circular. Maybe your quad is a rectangle and it's just the model you're going to build inside of it is circular. That would be another way to rationalize that too. And it makes a little more sense that way, in my opinion. And it measures 240 yards in diameter. So we've got this circle, and the diameter, which is the distance from end to end going through the center, that's 240 yards. Okay, so that distance is 240 yards. And we are going to fit the entire solar system into this circle, and we're going to use these given values, which are true as far as I know. I've only checked a few of them because I figure if the first 3 are right, then the rest are right. But don't take me to the cleaners over that checking. So they say that Mercury is 57.9 from the sun. So when they say orbital radius, that means how far it is from the sun. Now they have planet Pluto. Pluto is not a planet anymore. Also, it doesn't have a circular radius, so there's a couple of minor issues there. It's also on a tilted axis. So I mean, you could just say, well, Pluto's not a planet. We're going to ignore it, but let's not get into all that science and stuff. We're gonna go and pretend it's still a planet, I guess. All right, so Mercury is 57.9 from the sun. 57.9 what? That's not a QR answer. Oh, millions of kilometers, not just kilometers, millions of kilometers. If Mercury was 57.9 kilometers from the sun, it would probably just catch on fire and just, you know, be eviscerated. That's what I was trying to say. So Mercury is 57.9 million kilometers away. Venus is 108.2 million kilometers away. Earth is 149.6 million kilometers away. So we can see that these planets are getting further and further away from the sun. So they are in order, in that traditional order of distance from sun to furthest out. So what they will say is, we want to create a scale model of the solar system on the quad that is circular and measures 240 yards in diameter. And we're going to scale Mercury to 1 yard. This is our decision. We said, all right, in this, we want to make, let's say our center is right here. We want to put Mercury, I know Mercury's not green, bear with me. We're going to put Mercury right here. And this distance right here is going to be 1 yard. And then here's its orbit. And then Venus is going to be some distance further away. So maybe Venus will do in this little dark red. So maybe Venus is over here, a little further away. I'm just going to go V for Venus. Here's its radius. And then we're trying to figure out what this distance right here would be. That is what would go here. That's not 0. I'm just saying it's what would go there. And then we're doing the same for all the rest of the planets. Now, I'm not going to fill all of these out. I'm only going to do a few of them. I might leave this for a quiz. I might leave it for nothing. I might just say, hey, I would highly suggest that you finish this on your own and be good students because it's excellent practice. That's probably what I'm going to do in this instance, since I already have a quiz assigned for today and I don't like going back. Okay, so if you set Mercury to 1 yard, what is the model scale you are using? So what they're asking has everything to do with Mercury and will end up being used throughout the rest of the planets. Now, before we move on, actually, I just need to clear my screen. Go, we're off of annotate. Okay. So here's what we want to do for the scaling. The two things we're talking about are the model and the actual. The model and the actual. So the model's distance and the actual's distance. So we have our model and then the actual. You can even be super specific and say the model is in yards and the actual is in millions of kilometers. All right, so these are the words, and then we just use up the numbers. Well, for the model, we said it was going to be 1 yard. So where does that go? That goes in the top. So the 1 yard goes in the top because that's what we determined, what we decided the model distance should be, and we're hoping that everything's just going to fit in this 240 yards. All right, well, what was the actual distance to the sun? The actual orbital radius, same thing, 57.9 millions of kilometers. Well, there we go. So what is the model scale? It's 1 yard is 57.9 millions kilometers. That is the answer to A. Because when you use your words, apples over oranges, and then every 1 apple is 57.9 oranges, again, you don't have to think about these things in terms of anything complex. You can just always relate everything to apples and oranges, thing A and thing B. So that's the scale. For every 1 yard on our little quad circle that we're setting up, that would be realistically equivalent to 57.9 millions of kilometers, as long as we measure accurate. So then part B, use this ratio, this 1 to 57.9, to determine how far the other planets would be and fill in the table with 2 decimal places of accuracy. So how far away would you place Venus? How far away would you place Earth? How far away would you place Mars? Let's go ahead and get an idea of what the answers should feel like so that when we get the answers, we can ask, does it make sense? So Venus is further away from Mercury. So the first thing in terms of you asking, does it make sense? Let's say I got the answer as 0.7. That is trash because it's less than Mercury. Why on a scale that's supposed to be proportional, if the distance to Venus goes up compared to Mercury, why would on the scale would it go down? That's terrible. That would not make sense. Let's say I get an answer of 50. Well, the Mercury distance was 57.9. Let's just call it 60. Let's just round it to a kind of a cleaner number. And then 108.2, well, that's about 120, and I'm using the term about very loosely there. But I'm just trying to say this is about 60, this is about 120, or you could say these are about 50 and about 100. I'm just trying to get them close to a whole number apart in terms of a multiplier. So either way, what I'm trying to say here is these numbers are doubled roughly. The distance to Mercury versus the distance to Venus is about twice as much. 60 versus 120 or 50 versus 100. So I expect the answer over here to be about twice as much, so I expect it to be in the ballpark of 2. 50 is not in the ballpark of 2. It's not even close, so that would say I've done something terribly wrong. So it wouldn't make sense. All right, so we're in part B now. Let's actually do the math. So this is literally a proportion table. You can just do everything that way. So you can imagine yourself drawing your box around these 4 things. There we go. That's it. So we would go 57.9, not 8. I was looking at an 8, sorry about that, over 108.2 would be equal to 1 over x. And then you can cross multiply. The 57.9 would be multiplied by the x. And then the 1 times the 108.2 is 108.2. You then, to solve that, divide by 57.9. Absolutely no excuses in this course to not know how to solve that equation. Will not survive this course without knowing how to solve that. And then you pull out a calculator. Just this one today. And let me clear my screen since that's getting in the way now. So we got 108.2 divided by 57.9. And we get 1.87 when we round to the nearest second place. 1.87. 1.87. So that would be 1.87 for the distance from the sun to Venus. 1.87 what? 1.87 feet, 1.87 Bob Doles, 1.87 oranges, 1.87 million kilometers? No, you're not building a scale in millions of kilometers. You built it in yards. And that is about 2. It's roughly 2. And again, I'm not saying it's super, super close to 2, but it's pretty close to 2. So it makes sense. Earth. Well, again, this is about 50. This is about 150. So that distance triples. So I'd expect this answer to be in the ballpark of 3. Now, it's going to be less than 3 because 58 is closer to 60 than 50. So 150, it's probably going to be somewhere between 2 and 3, but closer to 3, or at least like halfway to 3. Oh, I'm on annotate again, that's why. Okay, so C. No, not C. Still in part B. And let me just switch that letter over here to V for Venus. And then for Earth, we'll make that a letter E. So we can imagine ourselves drawing our box this way, if you want to use proportion table. So 57.9 over 149.6 equals 1 over, and again, we're calling that E for now. So we got 57.9 over 149.6 equals 1 over E. Cross multiply, you'll get 57.9 E equals 149.6. Divide both sides by the 57.9. You get that E is equal to, rounded to 2 decimal places. Come on, calculator, you're killing me. 149.6 divided by 57.9. And we get, does that answer make sense? No, it doesn't. 0.25. That doesn't make sense. And if you can see, it's really teeny, but when I hit my decimal, it didn't actually register. So I made a calculation error. That's just a tiny little boo-boo, but I knew it was wrong because the answer didn't make sense. If you just blindly trust everything and you're not asking yourselves, you're going to write 0.25 as the answer here, and then you're going to get it wrong. So let's try that one more time. Let's be careful, 149.6. And this is why we do things twice when we're on our own, 0.9. Now 2.58, that answer makes much more sense. What the heck? That didn't make sense. 2.58. I'm actually learning why that happens. So 2.58 yards is how far away Earth would be. Then if you wanted to do Mars, you can see that you're going to end up doing 57.9 over. So just imagine extending the box down to here. The top row just keeps getting used. Now you don't have to. I could draw my box this way if I wanted to, because now I have the Earth number. I could certainly draw this as my box. Let me clear my screen first. I could certainly draw this as my box since I know the Earth value, but I've always suggested that you shouldn't use borrowed information if you don't have to, especially if you're rounding that information, because rounding leads to further errors along the line if you keep doing this over and over and over. So 57.9 over, where are we, 227.9 equals the 1 over, now we're talking about Mars. We used M for Mercury. Let's go R for Mars. So R, the third letter of Mars. Cross multiply, you end up getting 57.9 times the Mars variable equals 227.9. You're going to end up dividing both sides by 57.9. And this is another reason I like to keep using the top row, because we keep doing the exact same algebraic step. And if you pay attention, why did I show it that way as a fraction? If you get used to the repetition, you'll go, oh, okay, well, I take the Jupiter number and divide it by the Mercury number. I take the Uranus number and divide it by the Mercury number. I take the Pluto number and divide it by the Mercury number. It would get you the answers a lot quicker. It would be efficient. All right, so 227.9 divided by 57.9. And we get 3.93, which is further than Earth was, but it's not some extravagant number. 3.94, actually, if we round appropriately. So 3.4 yards. So I'm going to very quickly say the answers to the rest of these. I'm not going to make this a quiz, but I do encourage you to do these on your own. I'm giving you the answers for what reason? It's not a homework. It's not a quiz. I'm giving you the answers so you can try it out as practice, because this is one I love doing group work on, but group work just doesn't work for us. So the asteroid belt ends up being 11.85. Jupiter ends up being 13.44. Saturn ends up being 24.69. Uranus ends up being 49.65. Neptune ends up being 77.80. Pluto ends up being 102.17. If that went too quick, go to YouTube, pause, play, pause, play, pause. And that is really all I want to do with this section, aside from making one extra little statement. So let's take off, let's clear the screen. Clear the screen, there we go. Annotate, drop that. I really wish my Windows button worked. I mean, I really wish I didn't have to hit the Windows button so much. It's kind of tedious. Here we are. All right. So some scales, I would actually say most scales. You know what? I don't want to use most. We'll say some. Some, maybe most scales have units. Some do not. A unitless scale implies that the units of the model are the same as the units of the actual. So when we were just doing the planets, that had units. Inside of that scale, if you wrote everything out meticulously, it's one, let's say 1 inch is 72 feet. So that would have units there. Or for our planet problem, oops, wrong thing, this. We said that it was 1 yard was 57.9 millions of kilometers. Now, and when I did these as proportions, I didn't have to do them that way, as I mentioned but didn't go back to. I could have, this is just the proportion equation. We could have just thrown the actual into that, and we would have gotten the same answer. So when we wanted to do Venus, we could have just replaced this with the 108.2. When I wanted to do Earth, I could have just replaced this with the 149.6. When you want to do Neptune, you can just replace the actual with 4509. So I did this as a proportion table, but you can still do this as this scale equation. You can also do it as the y equals kx setup, but it's not as simple as you might think. So that's why I'm not going to talk about it for this particular problem. So again, some scales have units like the one we just practiced with the planets, because one thing was in yards and the other was in millions of kilometers, but some scales do not. So if I had a model where I said 1 foot is 72 feet, so I take a 72 foot, I don't know, Mack truck, and I scale it down to 1 feet, 1 foot, 1 feet, 1 foot singular, that would be a unitless scale because they both have the exact same units, which means I don't have to say 1 foot is 72 feet. I could also say 1 inch is 72 inches. I could say 1 kilometer is 72 kilometers. I could put any units I want as long as they're a distance unit, and it would be true. Now, yeah, I may have been taking a 72-foot trailer and putting it down to 1 foot, but the conversion factor is still exactly true if you did it in yards or meters or kilometers or inches or centimeters or whatever you like. So when you're scaling from the same units, it's called a unitless scale or unitless model. So that is 3.2. We are not done for the day, but we can go ahead and say that 3.2 my math lab is going to be due a week from today, which today is the 13th, so that's the 20th. All right. 3.3, a longer section. And yeah, I don't need to say and. Rates. We have talked about rates lightly already. When we talked about miles per hour, we said that that was a rate. We've talked about the word per many times already and how it means that the next unit goes in a denominator. So those things were rates, and we're going to start studying them a little more explicitly. We're going to talk about ways that we can effectively use rates like in the grocery store to do a cost analysis. Not necessarily just at the grocery store, you can do it anywhere. But that's one of the things that I would love for you to take away from this course, not just because it's cool math, but because it's something you can use every day. If you want to say, all right, I got this brand of candy versus this brand of candy, and I want to know which one's cheaper. Well, okay, well, this one is $3 and the other one's $4, so obviously the one that's $3 is cheaper. Well, not necessarily, because maybe the $4 one you get a pound of candy and the $3 one you get 2 ounces of candy. So yes, it's going to cost you less to buy the $3 thing versus the $4 thing, but you're going to get proportionally more with the $4 thing, or more than proportionally more, in fact. So it would make it more cost effective. Or maybe you go, okay, well, I really like Chick-fil-A sandwiches and I eat one every day and it costs me about $4 after tax. Or, so one Chick-fil-A sandwich is $4. So on Monday, you're like, I could go to the grocery store and buy a bunch of chicken and make this for the week. I found this recipe on YouTube to, you know, I got the pickle brine, I got the breading, whatever, all that jazz, the peanut oil. And you say, okay, well, I could just do this at home. Maybe that'd be more cost effective. You go, well, no, if I go to Chick-fil-A, it's going to cost me $4 for the sandwich. But if I go to the store, I got to buy 2 pounds of chicken breast, and that's going to be, I don't know, $9 or $10 unless you're buying the super cheap stuff, which is fine if you are. Maybe it's only $5. And then you got to buy buns, and you got to buy the pickle brine and all that other stuff. So you go, well, no, it's cheaper to just buy the $4 sandwich. But then on Tuesday, you got to buy it again. And on Wednesday, you got to buy it again. On Thursday, you got to buy it again. And Friday, you got to buy it again. Whereas if you made 5 of these all at once on Monday and froze a few so that your chicken doesn't go bad, Okay, yeah, it might have cost you like $12 or $13 to buy all the ingredients and stuff, but it's going to last you 5 days versus that sandwich that's $4 only going to last you 1 day. So yeah, it's going to cost you less on Monday to buy the $4 sandwich instead of the $12 of ingredients. But by the time Friday rolls around, you're going, whoa, I'm spending more money. This actually does suck. I should have bought the stuff myself. Whatever. Okay. So rates are a ratio of two different types of quantities. So rates have to be two different types of quantities to call it a true rate. Now, yes, in the world, you can call a rate a ratio of two of the same thing, and you can let that slide in the same way that when I say it's 72 degrees outside, that's not technically correct. It's 72 degrees Fahrenheit outside. So when we talk about rates in the classroom, we're going to talk about them being different units, comparing apples to oranges, comparing students to teachers, comparing distance to time, comparing miles to hours, comparing feet to seconds, comparing kilometers to days. And all of those last 3 or 4 that I said are actually the same thing. It's just that one I labeled with actual dimensions and the other I labeled with their literal quantities. So distance and time would be the actual quantity types, whereas miles per hour or feet per second or kilometers per day, those would be labeled with units. Now, it doesn't matter how you label them as long as you give them an accurate label that you can use and repeat accurately. So cost analysis can be as simple as a rate. And that is the problem that we're going to work through here. Cost analysis. Cost analysis is a rate. It's a rate of two different things. It's a rate of, well, the cost, I feel like that's obvious, to how much you get. Cost analysis is a rate, it's a ratio, it's a fraction of cost to how much you get. So if you pay $10 and get one item, then that ratio would be 10 over 1, and it would be $10 per item because you'd have to have all those units in place. But if it costs you $10 for 10 items, then that means that it would cost you $1 per item. So maybe at the store, they've got this super, super high quality product and it costs you $10, and in that thing you get one of the items. And then you've got your much lower quality but still functional and usable item that you pay $10 and you actually get 10 of them in the package. So the first thing would cost you $10 per item because it costs you $10 and you get one item, whereas the second thing, the cheaper thing, ultimately, would cost you $1 per item because it's a $10 cost divided by 10 items. 10 divided by 10 is 1. So that second thing would be more cost effective because you can get 10 of them for the same price that you can get one of the other thing. Now, when we talk about how much you get, you can talk about this in, maybe it's the number of candies, maybe it's the weight, maybe it's based on the size. It just depends on the context of the problem. Now, what's cool is a lot of grocery stores actually put what we call a unit cost. Well, let me give myself a little more space here. Select, boom, here we go. Come on, thank you. So this is what we're boiling down to. Cost analysis is taking the cost and dividing by how much you get. Unit cost is the cost divided by how much you get. It's the cost per item. Or the cost per gram. Or the cost per maybe square foot if you're talking about buying floor tiles, something like that. Relevant to my life right now. So that's unit cost. Now, in the previous example I just verbally went through, we had one item that cost $10 and you got one of them, and then we had another package of items where it cost $10, but you got 10 of them. So the first thing costs $10 per item, the second thing costs $1 per item when you do that division. Which sounds better? Well, the $1 per item. You want this as low as possible. Your goal to be cost effective is that we want this as low as possible. So if we're comparing two products, whichever one is lower is the better unit cost and the better buy. Now, I'm not talking about quality of the item. I'm not saying that the thing that you got 10 of, they're not just going to break almost instantly and maybe you should have just bought the more expensive item. I'll find that if you're going to do any kind of plumbing, metal costs like 2 to 3 times as much as plastic, but you're going to break that plastic 6 to 12 months later, especially if you got kids. So you buy the more expensive item there, unless you just want to keep replacing it. But you know, a lot of people don't have those options or just need to keep things as cheap as possible immediately. I don't know. Doesn't matter. Okay. Bulking on a budget. In fact, let me just do this. Let me bump. Will that move? Yes. Good. Good, good, good. Good. And the answer displayed. Bulking on a budget. You are trying to gain muscle mass, so you want to increase your protein intake. So you're going to the gym, you're lifting weights, but you can't just lift weights, you've also got to eat. And one of the main ideas to gain more muscle mass, besides ripping your muscles and letting them repair over time, is to increase your protein intake. So more protein, more muscle tears, more bulk. So you go to the local grocery store and you find one of those big jugs of whey powder, and the sticker price on it is $20 and it costs 32 grams of protein. And I did go to Kroger recently to research this. And it's $20 and it has 32 grams of protein per serving with 12 servings total. So this is scenario A. You can buy a big jug of powder and that jug is a $20 sticker price. And there's sales tax involved. Let's ignore the sales tax. Let's pretend that we're in Alaska or Oregon, or there's 3 other states, but that's not the point of the problem. So we're in Alaska. Yay, Alaska. So $20 gets you your protein, and in that protein you get 32 grams of protein per serving. So there'll be scoops. You do 2 scoops, and it's 32 grams of protein. And there's 12 servings in that container. So it's not saying that there's 32 grams of protein total. It's saying that there's 32 grams of protein, and then there's another 32 grams of protein, and then there's another 32 grams of protein, and there's 12 of them in total. If you measured them out exactly, you would get 12 servings of this 32 grams. Second scenario is you find some soy protein bars. So we got whey protein and soy protein, and we're not getting into the science of whether whey is better than soy or vice versa. I'm just mentioning that these are the typical products. A lot of protein bars are soy. There are whey protein bars. There are other protein bars out there that aren't whey or soy that you can actually get egg protein and animal protein, things like that. But again, not the point of the problem, but nutritional information, very important. Study it in another class. And I would love to teach a little bit of that, but that's not what I have my degree in, so I don't. So you find these soy protein bars that cost $8. Oh, wow, I'm going to buy those, right? Because 8's cheaper than 20. So when I'm thinking in the moment, 8's cheaper than 20, let's go with the protein bars. Well, hold your horses. Let's think about this mathematically. So with these protein bars that you're paying $8 for, each bar is 20 grams per serving or per bar, whichever way you want to phrase it, and there's 6 bars total. So each bar, each serving has less protein, but you could always just eat like a little bit of a second bar if you wanted exactly 32 grams, or maybe from the whey protein, you just scoop a little bit less and you try and measure out 20 grams of protein. Again, the delivery is not the point of this. So if all you care about is getting your protein as cheap as possible, which do you buy? So all we care about is getting it as cheap as possible, not about getting 32 grams versus 20 grams, not about whey versus soy, just cost analysis, pure, unadulterated cost analysis. So you want to keep this ratio of cost to grams of protein as low as possible. Remember, unit cost is the cost to how much you get of it. We don't want to compare the cost to the total weight in this instance because we don't care about the total weight of the product. We don't care how much fat or how much carbs are in this. We're only caring about the protein here. So you wouldn't want to just compare it to the pure weight of it. You would need to go specifically to the weight of protein. Now, maybe you're thinking, I just want as many calories as possible, and then you could just go strictly to the weight, or you could go use calorie numbers. The weight number is arguably not valid for calorie consumption as well, because you can have empty, I don't want to say empty calories, but weight that doesn't actually produce the same number of calories because they're not distributed evenly. Science, that's all. So you would just use the calorie number instead. So you'd go cost per calorie, but we're going to go cost per gram of protein. But there's a problem here. How much protein do we actually get from each item total? We don't know. We weren't told. I told you get 32 grams per double scoop of protein powder. I told you get 20 grams of protein per bar. But how much protein is in the package of bars? How much protein is in the container of powder? Because it's not just one serving. It's not just 32 grams. There's 12 servings. It's not just 20 grams total in a single bar. There's 6 bars in total. So you've got to do some math. Now, some people will automatically know, oh, you need to multiply the 32 and the 12 and the 20 and the 6. But some of you might be thinking, well, maybe I need to divide them, or maybe I add them, or maybe I subtract them. So here is what opens an entire world of mathematics that we already started with dimensional analysis. It's the idea of, I think I might have said this in the past, math on the back of a napkin. If you can take some numbers and with units, multiply and divide them in such a way that the answer you get has the units you need, the answer's probably right. And that seems extremely far-fetched, and yet there are entire books of mathematics written on that. So just think about taking, for the powder, caps on clearly, the total grams of protein should be equal to. So the two numbers we're dealing with for the powder, let's highlight it for now, are the 32 grams per serving, and then it's 12 servings total. Those are the two things. So what I'm suggesting to you is that if you can write these numbers with their units in appropriate places and multiply or divide them in such a way that the answer has the expected units of what the answer is, then you're good. So let's see, 32 grams of protein per serving. Let's just write that. 32 grams of protein per serving. The word per means it goes in the bottom. So it's grams per serving. The word per here is extremely important. I've said it many times. I've written it at least once. Per means the next unit goes in the bottom. Then we have 12 servings. Now, if you try to divide this, it would look really weird. So let's try multiplying it. I say it would look really weird, and you would end up with grams per serving squared. And that's the same idea as we saw in the very beginning of 3.1. I don't want to do that just going around in a circle twice, though. So if you take the 32 times the 12, you'll get a number. And it's 384. Now let's see what the units do. We have the grams. The grams are still there because it didn't cancel anything. We have a serving at a bottom and a serving at a top, so they cancel. So the total grams of protein is 384 grams. This unit is the expected unit of the answer. There's no serving written anywhere. 384 is an answer that makes sense. If it's 32 grams per serving, you could literally just count them out. 32 for the first, 32 for the second is 64, 32 for the third is 96, and just add up 32 12 times until you run out of powder and you get 384 grams. So again, this idea here, that if you just multiply or divide numbers with units in a way that your answer has the units you'd expect and the number makes sense, it's probably right, and this is definitely right. So that's the total grams of protein. There's 384 grams of protein, and we don't have to do them 32 grams at a time. We could measure out 20 grams of protein. We could measure out 15 grams of protein. We could eat half the jug in one sitting if we really wanted to, and get about 200 grams of protein. What's that, 198? I'm sorry, 192. I don't know why I said 8. 192. Okay, so then the unit cost be equal to, we take the total cost, which is the $20. We divide it by where is it? How much we have, which how much we have is 384 grams of protein. So we take 20 and divide by 384. 20 divided by 384. And we get 0.052 blah, 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 blah. Now, this, you might say this is a cost, so let's just round it to 2 decimal places. And I will say that usually works. But if two things are really close to unit cost, you may actually have to go to 3 or even 4 decimals to see which one's cheaper. But this answer, spoilers, it will be good enough. So it was 0.05. And now you could write it this way, but it just looks a little weird. So let's write it as 0.05 per gram of protein. This is just laid out a little better. So that protein powder, when you boil this thing down to just 1 gram of protein at a time, it's costing you about 5 cents per gram of protein. Well, now let's try out the, oops, spoiler alerts, bars. We got to find the total grams protein. And we already saw what to do, so we're just doing the same thing here. It was 20 grams per serving. Per means it goes in the bottom. And then times how many servings? Well, we had 6 bars. Now, I don't want to write servings in the bottom and bars here. Use your words consistently. So if you put 20 grams per bar and then times 6 bars, you'll see the same cancellation. Cancel, cancel. 20 times 6 is 120. Not going to pull out the calculator for that. The only units you have left are your grams. If you had 20 grams per bar, 20, 40, 60, 80, 100, 120. The answer makes sense. Giving us a unit cost of, you take the, how much did we pay for the bars? I think it was 8. Let me confirm. Yes, it was $8. That was the total cost. And then per, so 120 grams of protein. And we do 8 divided by 120. 8 divided by 120, 0.06 something. 0.06666666, which rounded to the nearest penny would be 0.07. So 0.07 per gram, but it's just better written as 7 cents per gram of protein. So again, if you only care about which thing has a cheaper unit cost, which one will cost you less money over a long period of time, you're going to want this one. This is cheaper. So you buy the jug of powder. Now, when you go to the grocery store that one time, it's $8 versus $20. You go, Mr. Beckner, that's not right. I just spent $12 more. But guess what? If you only buy one thing of bars, if you're eating a bar a day, you're going to have to go back to the grocery store in 6 days. Or maybe you're eating 2 bars a day, and then you're going to have to go back to the grocery store in 3 days. And then you're going to pay that $8 again. Or maybe you just buy 5 or 6 or 7 boxes all at once, and then you have that cost multiplied by it. So yes, it's cheaper to buy 1 box of bars versus 1 jug of powder. But if you're on a regimen that you're going to do over a year, maybe you're trying to intake 50 grams of protein with this stuff a day, on top of your grilled chicken and whatever else you're going to eat. If you're consuming 50 grams a day, that cost multiplied over 365 days, you're going to end up spending maybe an extra 20 bucks on the bars, maybe an extra 100 bucks on the bars, but it would be significant. It's not going to break the bank, but it would be significant. So you can take this and you can compare, milk in one thing. So maybe one brand has the milk in a half gallon and the other brand has the milk in only quarts, or maybe one brand of milk has it in gallons and the other only has it in half gallons. And you go, well, obviously the half gallon's cheaper. It's $1 less or $2 less. Well, when you do this unit cost analysis or cost analysis, however you want to say it, maybe it turns out that the larger thing, even though it has a higher sticker price, is cheaper per unit. Now, if you're buying food and you don't eat it all and it spoils and you throw some away, that changes the game. So make sure that you're actually using everything. Don't be wasteful. Someone just pulled up to my house. Give me 5 seconds and make sure I can ignore them. It always throws me off when a delivery person actually pulls into the driveway. It's very unusual. Okay. We are not ready for 3.4. Not even close. That's too far. We're going to go back to the guided activities. Oh. You can see there's actually an Excel homework that we're not going to do because it has a lot more answers than usual, I think, that relates to what we were just talking about. We're going to go up to, here we go. This is an assignment that I have alluded to in the past. And again, it's just not enough answers to make a discussion board out of this with a large class. So we're going to work on this together. In 2011, nearly 14 million monthly prescriptions were written for American adults aged 20 to 39 for ADHD. If there were 82,364,000 adults aged 20 to 34, compute the following. The rate per adult aged 20 to 39 with 3 decimal accuracy. Then if we divide 14 million prescriptions by the rate from number 1, what are the units of the answer? The rate of the prescriptions per 100 adults in that age range, the rate of prescriptions per 1,000 adults in that age range, the rate of prescriptions per 100,000 adults in that age range. And then they ask us, what rate do you think is best? Now, this last question is subjective. So it's saying between answers 3, 4, and 5, which one do you like more? So we'll get to that later. In fact, we probably won't. Let's see how far we can get. I might just have to go a little quick. And I'm just going to use my ugly annotation in the interest of time. Okay. So the rate per adult. So first of all, this number right here is our first instance of a goofy number. Why is it goofy? Well, it's goofy for 2 reasons. First of all, this number up here talking about people is 14 million, and then this number talking about people is in thousands. Why did they give us millions of people in one value and then thousands of people in another value? You know why? To mess with us, to make us think and to make us be careful, because that's what the media does. They screw with us. So this is our first instance of inconsistent units between the same type of quantity. I would say normally, if these numbers are close to each other in terms of size, if one's in millions, the other should be in millions. If one's in thousands, the other should be in thousands. The second reason this number, the one I have circled or boxed right now particularly, is wacky, because if I was going to say something in thousands, we normally have like 15,000 or 700,000 or 32,000 or 82,000. We normally don't have 82,364,000. Notice how I said that. Pay attention. 82,364,000. I said the word thousand twice. That destroys people's minds. So you think this number is 82,000. It's not. It's much more than 82,000. So let's just turn these numbers into what they would be without the words millions and thousands. So 14 million would be a 14 with 6 zeros. That's 14 million. 82,364,000, the word thousand says to add 3 more zeros. So it's 82, 364, 000. So really that number is 82,364,000. So yeah, you can say 82,364,000. Nobody likes saying the word thousand twice or the word million twice. It's a horrible idea. It confuses people to no end. So if you want to write a confusing media article, do something like that. So looking at the text, it doesn't look like these numbers are that close, but in reality they are. 14 million, 82 million. No, they're not super close to each other, but I'm just saying they're in the same types of units in terms of size. So they want to know, what is the rate per adult, the rate of prescriptions per adult in the age range? So we're going the rate of prescriptions to number of adults. Rates are fractions of two different types of units. The rate of prescriptions, they don't actually use the word prescription here, which I think is poor form on their part. So the rate of prescriptions per adult. Well, there were 14 million prescriptions for 82 million adults, so that's what they're asking us to do. So 14 million over the 82,364,000. And when you pull out your calculator, when we do 14 million divided by 82,364, everything look good? Yes. We get 0.1699, blah, blah, blah. They say to round this to 3 decimal places. 0.169, that second 9 tells us to round up, which tells this 9 to go to a 10, which says this 6 goes to a 7. So even though it says 3 decimals, oops, I forgot to take annotate. Put the annotate back on. It's going to be 0.170. And that would be prescriptions, because that's the units from the top, and the bottom was adults, so per adult. So 0.17 prescriptions written per adult. So that says if you have a person, there's a 0.17 chance, if you think about statistics really, or probability, that that person has a prescription for ADHD if they are in the appropriate age range. Now again, we're only talking about that age range. Step 2, they say if we divide 14 million prescriptions by the rate. By the rate means that the rate is what's going to go on bottom. From number 1, what are the units of the answer? We're still on annotate? Yes, we are. If we divide 14 million prescriptions, so if we take 14 million prescriptions and we divide it by the rate that we just got, which is 0.17 Rx per adult. So that's 14 million prescriptions. We want to use our units because we're good QR students. And we're going to divide this by 0.17 prescriptions per adult. Now, here's where things get weird. In fact, let me do this in blue. 0.17 prescriptions per adult. So this is a division, the 14 million divided by the 0.17. But the units in the bottom are not just a single unit, it's a fraction. So what we really need to do here is write this in a slightly different way. It might be better to write this as 14 million. I think I have the right number of zeros. I hope I have the right number of zeros. Yes, I do. Prescriptions, and then over 1, then divided by the 0.17 prescriptions per adults. This is a division of fractions, fraction divided by a fraction. You are supposed to be coming in here with the knowledge of how to divide fractions. But you probably want to change this to the old school form of 14 million prescriptions over 1, then division symbol by the 0.17 prescriptions per adult, which would give us 14 million prescriptions over 1 times, and let me change color to show that emphasis, times, we flip it. The adults go in the top now, and the 0.17 prescriptions go in the bottom. So here's what happens. This prescription unit ends up canceling that prescription unit. The only units you're left with are adults. So whatever this number is, this 14 million divided by 0.17, let's go off of annotate. 14 million divided by 0.17. We end up with 82,352,000. Now, because of this 0.17 being rounded, this isn't exactly it, but it is pretty close. It's about 82.352.941 adults, which again is very, very close to the number of adults. The only reason it's not exactly the same is because we rounded the 0.17. This was rounded. If I left this as 0.1699, whatever the rest of it was, then it would actually give us the exact number of adults. But it's very difficult to use that exact number for obvious reasons. So the rate of prescriptions per adult is 0.17. If we divide, we end up canceling the prescription units and getting the number of adults. So what this shows is we took the 14 million prescriptions and the rate, and we did something with them to get an answer, and the answer was something we had already seen. So that these two numbers divided versus these two things but divided, there's a strong relationship. If we had decided to instead, well, what happens if you multiply? If you multiply this 14 million prescriptions by 0.17 prescriptions per adult, you're going to get a nonsense answer. You would get 0.17 times 14 million. You'd get 2.3 million and some change, but the units, you would have prescription in the top twice, so it's prescription squared and then adults. So there's 2.4 million prescriptions squared per adult. I have absolutely no idea what those units mean, so it doesn't make sense. So sometimes you'll be multiplying things together and get an answer that has units that make sense and you're done. If you did the multiplication and you got nonsense units, try dividing them instead. That's that clue of that whole math on the back of a napkin. So I tell you what, in the interest of time, we are going to stop there. We'll come back, and the first thing we'll do next class is 3, 4, 5, and 6 from this activity. 3, 4, 5, and 6. I've got to write that down so I remember.
In which I did. So again, that's what we'll be starting with at the top of next class, finishing out this section, and then we'll go on right into the next. So we haven't technically finished 3.3 yet, which is why you don't see a due date coming up. Obviously, you don't actually see the due dates, but you know what I mean. But we will get to that next time, as well as getting through the majority of 3.4, but again, not quite finishing it. We tend to have these little cliffhanger endings in a lot of sections. So we're going to go ahead and call it a day. Have a good one, and we'll see you soon. If not in, I'm sorry, we'll see you soon. I don't know what I was about to say.